It's a bit less ideal. I've had to resort to using my phone camera because anytime I do anything in this window, it doesn't show any of the daughter windows that appeal. So I have a data file open here. This is a 3-inch, 1300 nanometer-ish sample, indium phosphide. I'm displaying 4 maps for the peak wavelength, the peak intensity, the integrated signal, which is just the area under that, under the curve, and the full width half max, which again can be configured to be other than 50% should you desire. So I can right click on here. I can mess with the scale used. In this case, I'm set the average value for the center, and I've got a bin size, so each color band represents 1 nanometer deviation from that, and that's pretty much the limit of the monochromator's resolution in this manner. So that's a sensible way to have that configured. I can adjust the color scheme. I can adjust the units between nanometers or electron volts for the case of a wavelength. I have more parameters I could view in addition to the 4 I've got there. Lambda plus and lambda minus are just where the full width half max hits the curve. And the alloy composition, if I had a tertiary material set up, I could look for, say, the composition of indium in indium gallium arsenide, for example. The info button here will give us a list of the results and the statistics from this map, and it will also give us all of the measurement conditions used to acquire it. So if we want to go back and reproduce that in the future, that would be possible. In principle, you would save all of this into a recipe in the first place if you were doing this measurement repeatedly. I can get a histogram of it, which is much the same as doing the scale. I can get a line profile, how it varies across 2 arbitrary draggable points going across the map. The analysis window lets me tinker with things like the edge exclusion values and thresholds to be counted as real data. I can reprocess it to use some slightly different parameters. I can rotate it. I can zoom in. I can get a 3D view, and I can view it from the back of the wafer. As I've mentioned, it is possible to map indium phosphide wafers upside down with a 980 laser. So we'll have a quick look at this analysis window, and I'll apply an exclusion zone of, let's say, 4 millimeters to this. I apologize for the camera shaking. I can set, I've done that. I can analyze that and update it. I can do other things in that map. If I had a half wafer or partial wafer, I could set a threshold on the intensity and make sure that only data is taken within what we consider to be a real part of wafer was actually analyzed statistically across the whole map. So I can also pick an arbitrary point on here, double click, and it will give me the option to move there or to display a spectrum there. So this is roughly in the middle. It tells me the position just here. I can double click around and it will update that view as we go. And I can look at the parameters used to assess that. So we're using what's called a threshold analysis to find that peak, which means that our customizable threshold, which is set to 90%, we will find the midpoint at 90% to define the peak position. We have 2 other modes, so there's a standard mode and an integration mode. In the standard mode, this curve is made up from, in this case, 256 data, 128 data points across here. So in that case, the only allowable values are roughly every 1 nanometer. And you can see it's indicating where my cursor is at each point there. In the threshold analysis, I'll get a continuum. So there are data values allowed between the bins. I can get the information. So here's our statistics, and those will reflect the current situation. So the standard deviation of 0.136% on there is in here. Before I applied that exclusion zone, that was slightly higher because there were a lot more excursion points within the scan here. This will tell me how it was taken. So it was taken at 20 data points per second with a grid of 1 millimeter on a 3-inch 76mm scan. And the center wavelength was set to 1297.7 with a the resolution of 1 nanometer is a derivation of what is the detector and what is the grating. The detector in this case is an InGaAs array. They've used a 1100 high-pass filter to remove any residual 980 from the PL emission. We've used a 980 diode laser, probably set to about 7 milliwatts, and the temperature is recorded as a fairly cool 17.5. It has been smoothed. The recipe file used is listed there, and then there's a no wavelength correction applied. And then we can mess with the analysis mode and things like that. So if we want to change it to the other peak find mode, for example, we can reprocess the map, select standard mode, reprocess, and that's changed the standard deviation here by a very tiny amount. We can also save this as, for example, our native binary data file is this SPM spectral map. We can select an ASCII data file, and then we have a number of options for that. We can have it as an XY data array, which will just be numbers from this map exported. So we'll get 4 different parts to the data file with positions and value. Data columns will be similar, and then complete spectra would export an ASCII spectrum you'd end up with a very large file saying a position and then some ASCII data of the curve at each position. So that's basically a full data export. We can also save it as a picture file if that's desirable. And that's the bulk of the data analysis. So the statistics in that information box would be saved as what's called a report file. So you can configure in the recipe whether we get a report file, and that's a text file with an easily parsed format. So you can retain your measurement conditions and all the statistical information there.